never got hurt. He knew just what to do. He ducked and covered, ducked and covered. He did what we all must learn to do. You and you and you and you. Duck and cover.
Timmy, what are you doing?
Well, I'm ducking and cover, mister.
Why are you doing that?
Because there's going to be an atomic bomb, mister.
Did you know that ducking and covering would not save you from an explosion?
What?
Anyway, that's not why I'm here to talk to you today, Timmy.
Why are you here then?
I'm here to teach you about physics.
Physics?
That's right, I'm here to help you with your physics mush.
My physics mush?
Yes,
I do need help with that.
Well, I'm here to help you. So let's get started.
Okay.
Well, what do you need help with, Timmy?
I just need help with physics in general.
Well, let's start out by learning about gravity.
Gravity?
Yeah, gravity. It's the force that brings all objects down at a uniform acceleration.
What?
Yeah, watch.
Ow!
See, that deodorant was pulled down towards you by gravity.
Gravity?
Yeah, gravity pulls down every object in physics at an acceleration of 9.8 meters per second.
That's so
squared.
Cool!
Now let's go see how it works. Alright, Timmy. Here's a video of you dropping the ball. When you first drop the ball, it has no velocity. That's its initial velocity, 0 meters per second. However, when it hits the ground, it has a velocity of 5.88 meters per second. Now, in the 0.6 seconds it traveled down to the ground, do you know what caused it to accelerate?
Was it gravity?
That's right, Tim. And now, if we do the equation, the final velocity is equal to the initial velocity plus the acceleration multiplied by the time, we can figure out what that acceleration is. It's negative 9.8 meters per second squared. So now that we've learned about gravity, let's move on to motion.
Motion?
That's right. There's many different kinds of motion. You have horizontal motion, you have vertical motion, and then there's even projectiles.
Gee willikers, is that like an atomic bomb?
Well, sorta. Let's go find out more. Here we are at the bowling alley. This is a perfect place to watch horizontal motion in action. Watch as the bowler sends the ball down the lane. From this angle, we can get a better view of what's going on. Using the first two frames and the last two frames, we managed to calculate the initial velocity and the end velocity. Then, once we took those two velocities, we plugged them into our equation v is equal to VO plus AT. This allowed us to solve for the acceleration. The ball accelerated at a rate of negative 1.88 meters per second squared over a distance of 7.03 meters. Now let's hop on over to vertical motion. Watch our runner jump over the bar. See how he launches off? Let's figure out what his initial velocity is when he pushes off the ground. We can do this using our vertical motion equations and the acceleration we learned from earlier. We can solve that initial velocity is 3.92 meters per second. Our jumper's center of gravity traveled 0.89 meters for a total jump of 1.88 meters. Here we see the Imperial dropship prepare for battle against the rebels. As they use their cannons, let's watch the horizontal projectile missiles that are fired.
Horizontally, the projectile traveled 2.74 meters in 0.4 seconds. We know that horizontal motion remains at a constant velocity, so the acceleration is 0 meters per second squared. We plugged it into x equals VOT plus 1/2 AT squared to calculate that our final velocity was 6.85 meters per second, as well as our initial velocity. Vertically, the projectile traveled 1.2 meters and started at an initial velocity of 0 meters per second. Acceleration due to gravity accelerated the projectile at negative 9.8 meters per second squared. When we plug this into v equals VO plus AT, we find that the final velocity before impact is negative 3.92 meters per second. The cannon was fired at an angle of 26.92 degrees. Horizontally, it traveled at 3.33 meters per second, and the horizontal acceleration was 0 meters per second squared. The total time it took to hit the ground was 0.54 seconds. Vertically, its initial velocity was 0.9 meters per second and traveled a total distance of 1.48 meters. During that time, it accelerated at negative 9.8 meters per second squared due to gravity. We plug that into v equals VO plus AT to find that the final velocity equals 4.41 meters per second. We plugged all this into the range equation to find that the final horizontal distance traveled was 0.91 meters.
Now we're going to learn about what causes motion. Forces!
Forces?
That's right. There's many different kinds of forces, and they're all supposed to follow laws, called Newton's laws of physics.
Laws? You mean like those police things?
Yes, Timmy, sort of like police things. Let's look at them now. Alright, Timmy, let's begin by taking a look at Newton's first law. Newton's first law states that an object in motion will remain in motion unless acted upon by another force, and an object at rest will remain at rest unless acted upon by another force. In this video, we see this pop can moving along a table. It's given the force by the hand, stopped by the force of friction. Using the first two frames of the video, we calculated that the initial velocity was 1.45 meters per second. Because the can stopped, the final velocity is 0 meters per second. To find the force of friction, there was a couple things we needed to know. First, the mass. The mass of the can is 0.0156 kilograms. We needed this to find the force normal. Force normal is equal to mass times the acceleration due to gravity. So in this case, the force normal was 0.153 newtons. Now, in order to find force of friction, we need to set up the equation F of F is equal to mu times force normal. Now, since we already know force normal, all that we had to do was figure out the mu. And in this case, the mu was 0.15. When you multiply those two numbers together, the mu and force normal, you end up with a force of friction of 0.023 newtons. According to Newton's first law, if the friction had been non-existent, the can would have continued to move forever.
Newton's second law states that mass and acceleration are inversely related. We used a launcher that exerted a uniform force on both masses. Our first mass was 0.567 kilograms, and our second one was 1.701 kilograms. They both started at an initial velocity of 0 meters per second. Based on the last two frames, our first weight had a final velocity of 1.88 meters per second, while our second one had a final velocity of 1.33 meters per second. We plugged the values from our first weight into v equals VO plus AT to find that the acceleration was 14.14 meters per second squared, while the second one with more mass had an acceleration of only 7.96 meters per second squared. The fact that the second weight with more mass accelerated at a slower rate proves Newton's second law that mass and acceleration are inversely related.
Newton's third law states that every action force has an equal and opposite reaction force. Here we see little Timmy sitting in a chair who has a mass of 75.6 kilograms. To find the force of gravity, we multiplied mass times the acceleration due to gravity, which equals negative 740.88 newtons. Because his acceleration is 0, force of gravity is opposite force normal, which is 740.88 newtons.
Curious hooded man watches
From a distance.
Take a second to look awesome. Time to go walk in slow motion so you still look awesome.
Steven, get out of the shot. Steven, get off the roof. Get out of the shot. Come on. I guess we can work with this. So in this video, Steven's standing on the roof. The only thing keeping him up on the roof is static friction. Now, in order to solve for static friction, we need a couple things. This coefficient of static friction, which in this case is equal to 0.75, Steven's mass, which is equal to 68.4 kilograms, and the angle that Steven's standing on the roof, which is 12 degrees. From there we can calculate the force of gravity. Now, force of gravity, as we know, is equal to mass times the acceleration due to gravity. When we plug our mass in, it gives us a force of gravity equal to negative 670.32 newtons. Using trigonometry, we solved for force of gravity perpendicular and force of gravity parallel. Our force of gravity perpendicular was 655.67 newtons, and our force of gravity parallel was 139.37 newtons. Since force of gravity perpendicular is equal to the opposite of force normal, we can plug it into our equation. We find that force normal is equal to 655.67 newtons. Using this, we can then take force normal and plug it into our equation. Force of friction is equal to mu times force of normal. That will give us a force of friction equal to 492.5 newtons. In this situation, force of friction can apply up to 492.5 newtons, but in this situation, it's only having to apply 139.7 newtons. In this video, we see a very basic pulley system set up. 4 forces are at work. Force of tension 1 and force of tension 2, and force of gravity 1 and force of gravity 2. Because neither mass moves, the overall net force is equal to 0. Therefore, we can set up an equation in which the force of tension combined with the force of gravity is equal to 0. We know that the mass of each weight is equal to 0.567 kilograms, and we can use this mass to solve for force of gravity. In this case, the force of gravity is equal to negative 5.56 newtons of force. And since we already know that force of gravity is equal to the opposite of force tension, we know that force tension will be equal to 5.56 newtons of force. And now we're going to learn about another force, centripetal force.
Centripetal force? I thought it was centrifugal force.
No, Timmy, that's a made-up force. Yeah, it's a made-up force. Sort of like being able to survive an atomic bomb explosion by hiding underneath your desk.
What?
Anyway, let's talk about centripetal force and centripetal acceleration.
Swell.
Here we see
Stavros.
my evil twin swinging a 5.9 kilogram mass around a radius that is 1.34 meters at a velocity of 6.48 meters per second. The centripetal force can be calculated by mv squared divided by the radius, which gives us a centripetal force of 184.93 newtons. The centripetal acceleration can be calculated by v squared divided by the radius, which gives us a centripetal acceleration of 31.34 meters per second squared.
Alright, Timmy, now the last thing we're going to learn about today is work, power, and energy.
Work? That's a pooper.
Don't worry, Timmy, you won't have to take out the trash today. Let's go learn about it.
Yeah.
Here we see Steven jumping up and down on the trampoline. Let's calculate his GPE at the bottom when he's not moving.
My mass is 68.4 kilograms and I was at a height of 0.88 meters. To calculate my GPE, we multiply the mass times gravity times the height, which gives us a GPE of 589.88 joules. To find total energy at this point, we add GPE and KE. Because I'm not moving, my kinetic energy is 0, therefore my total energy equals my GPE, which is 589.88 joules. To find gravitational potential energy at the top of my jump, I multiply mass times gravity times height. My height is changed to 2.49 meters, giving me a gravitational potential energy of 1,669.10 joules. In this situation, my total energy equals my GPE again, because at the top of my jump, my velocity is 0, giving me no kinetic energy. You might have noticed that my total energy changed from 589.88 joules to 1,669.10 joules. Work is equal to the change in energy, meaning that the differences in my total energy equals my work, which was 1,079.22 joules. Power is equal to the work exerted over time. The amount of work I exerted was 1,079.22 joules over a time of 0.5 seconds, giving us a power of 2,158.44 joules per second. Now let's calculate the kinetic energy right before impact. To do so, we can subtract our GPE from our total energy to find our kinetic energy. To do that, we first need to calculate our gravitational potential energy at that point. Plugging in my mass of 68.4 kilograms and an acceleration of negative 9.8 meters per second squared due to gravity, and a height of 1.61 meters at that point, I find that my gravitational potential energy is 1,079.23 joules. When I subtract the GPE from my total energy, I find that my kinetic energy is 589.87 joules. We know that kinetic energy equals 1/2 mv squared, so I can find that my velocity before impact was 4.15 meters per second. Before calculating elastic potential energy, we need to know the K value of the trampoline. We used Hooke's law to determine this. Hooke's law states that force equals negative K times X. We placed a 27.22 kilogram mass on the trampoline, exerting a downward force of 266.756 newtons. When we placed this mass on the trampoline, the spring stretched 0.05715 meters. We plug both of these values into Hooke's law, which is force equals negative Kx, to determine the K value is 4,671.63 newtons per meter. From there, we can calculate elastic potential energy, which is equal to 1/2 kx squared. When I impacted the trampoline, I displaced the springs 0.74 meters, giving me an elastic potential energy of 1,279.09 joules. At this point, all my kinetic energy has been transferred into elastic potential energy, but I still have some gravitational potential energy left. To find the amount of gravitational potential energy left, we can subtract the elastic potential energy from the total energy, which is 1,669.10 joules. This gives us a gravitational potential energy of 390.01 joules. We can plug this back into GPE equals mgh to find that my height is 0.58 meters at the very bottom. Throughout this entire time, energy was conserved. At the very beginning, my total energy was 589.88 joules, which was all gravitational potential energy. I exerted 1,079.22 joules to have a total energy of 1,669.10 joules at the top, which was again all gravitational potential energy. Right before impact of the trampoline, my total energy was still 1,669.10 joules, but 1,709.23 joules was gravitational potential energy, and 589.87 joules was kinetic energy. At the very bottom, my total energy was still 1,669.10 joules, 1,279.09 joules if it was elastic potential energy, and 390.01 joules was gravitational potential energy.
Well, Timmy, I hope that presentation really razzed your berries.
It sure did, mister. Now I'm ready to go and do my physics mush.
Just remember, Timmy, if you don't do your mush, the communists win. Now, Timmy, you aren't going to remember anything outside of the 1950s.
Sorry.